Sorry, we're a little bit behind schedule. So next up, we'll have Alex Davies from DeepMind that will be talking about machine learning with mathematicians.
All right, we're looking good, mic on. Excellent, thank you very much. And we'll see if we can fire through. I don't want to take any time away from Kevin because he always gives excellent lectures, no pressure. So this is part 2, in a sense, of Geordie's talk from yesterday morning. So my name's Alex, I'm from DeepMind, and for the last couple of years we've been looking at how we can use techniques from machine learning to help mathematicians with pure mathematics. And in particular, one of the questions that we were trying to ask is whether we can use machine learning to help mathematicians discover a new mathematical structure. And so a real focus of this work was trying to see if there really was ways that we could use machine learning to find results that mathematicians genuinely find interesting. So really aiming at the forefront of mathematical research rather than a principled, ground-up way of learning mathematics from scratch. And while this is obvious to mathematicians, this was certainly not obvious to me before this, and may not be to you depending on your background. But there's this understanding that a lot of the advances in mathematics are not necessarily based on what we're used to doing in high school and in undergrad mathematics of kind of grinding through formulas, but it really is this kind of sense of insight that you see in mathematicians like Ramanujan, who had these formulas come to him in dreams, or these insights that come from very mysterious pattern recognition kind of places. And we know that pattern recognition is one thing that neural networks and machine learning in general are very good at. And so we're going to talk about a story of how we have the machines on one side doing things they're good at, helping mathematicians do things that mathematicians are good at. So our first paper that we're going to look at today looked into this in particular. This is this AI-guided intuition, which I feel landed reasonably well with the mathematical community for the reason that we were trying to solve problems that they care about. This wasn't trivial. Kind of mathematics was discovered 2,000 years ago. We were trying to see what machine learning can do at the current forefront of maths. So before we get into the particular results, as some context setting, the idea of searching for patterns in mathematical objects is definitely not a new thing. It's more about how we're doing it. So if you go back far enough, the prime number theorem is a good example of a theorem where the conjecture originally came about from observing data. And back in the day, you had to sit down for really quite a long time to manually calculate primes tables that you could then look at and notice a pattern that you could form into a conjecture. And then as soon as computers came around in the 60s, Birch and Swinnerton-Dyer were among the first to put forward a very truly famous conjecture that they used by getting early computers in Cambridge, calculating a bunch of examples of mathematical objects, plotting various quantities of them, and then observing this unusual and unexpected pattern manually by looking at the plots. And so what we're going to talk about here is taking the obvious next step, where we're not only going to calculate the examples, which we're obviously very good at now. We have huge amounts of compute in the world, and we can compute very large examples of mathematical objects and huge data sets that no mathematician could reasonably ever look at. And so we might also need some help trying to find the patterns in this data that we can then take away and use to form reasonable conjectures that mathematicians can then work with. So I'll lay out this framework about how we're going to talk about what we do here and what parts of maths fit into this. And to keep it simple, we're going to say that to start with in this process, we need to have a hypothesis that a function exists, an approximate function mapping between two spaces. And if we have that, a priori, something that the mathematicians would like to know whether a function exists, we can generate some data, and we can train a model to see whether or not we can approximate a function. And if we can, that's strong evidence that an approximate function does exist because we've learnt one. And if we've done that, we can use some simple techniques to try and determine properties of this function or kind of get an idea of what this function is doing so that we can conjecture ideally closed form versions of this function that a mathematician could use. And this is a kind of fluid back and forth process, so we can kind of refine what we're doing as we go along, as we find interesting things. So as a kind of quick canonical example, I like Geordie's tiger, but I think cute cats are better. I could have a hypothesis that there's this box, I place it in front of a cat, and the output that comes from this box, there is a function from this bit stream into whether or not there is a cat in the image. And I want a neural network to try and help me out with this. What's going on in this setup? If I really genuinely knew nothing about this, and if we train a neural network to predict a class of this image from the image itself, we would get something like this, as you might expect. Given an input image, after training, the network would return some list of probabilities against a particular class that is the kind of main class in the image. And we could train this function and it would do a good job. So this would tell me, okay, there does exist some function that maps from this bit string onto the existence of a cat or not in the image. So this camera thing is doing something sensible. And then a very simple technique that we can use, and there are other ones that would perform a similar function, would be what Geordie mentioned yesterday, which is called, in machine learning, often gradient saliency. The saliency maps in statistics, it's sensitivity analysis, but it's essentially taking the derivative of the prediction with respect to all of the input variables, and then looking for ones with high norm. And we assume that if we have a sensibly learned function, the function is going to be sensitive to any parts of the input which are actually useful for making this prediction. This turns out to work generally quite well in practice, and we can do this to our cat. And we will see that the pixels that we would meaningfully think represent the cat are the ones that the neural network is sensitive to when it's making this prediction. So if you were to change individually any ones of these pixels, this would have the strongest effect on the output prediction. And this is, kind of what we expect. And if I didn't know how to map this function from from the image pixels to cat, this saliency map would tell me a lot about what's actually going on there in this function. So we can take this concept and move it to more sophisticated results. And it's, I think, not a ridiculous analogy because mathematicians often are very visual thinkers. And so I kind of think of it as them being able to see cats in a way that I can't. But Mark and Andras there have very sophisticated visual understanding of knots and topology. And Geordie there similarly in representation theory. So I'll quickly go over knot theory as an example. That's a knot. These are all different kind of pictures of knots. Hopefully you guys are a little bit familiar with this. But the knot is roughly what you think of as a knot, but it's connected. So it's like a real life knot, but the two ends are glued together. And knot theory is a kind of intersection area of mathematics where a lot of different fields have something to say. Including hyperbolic geometry and algebra, and these are fairly distinct areas of maths when it comes to knot theory. And up until now, there hasn't been a lot of connection between these two areas directly. So obviously, for any given quantity, they're kind of trivially related through the topological object that we're studying. But in terms of how do you say things about the algebra from the geometry or vice versa, the only thing which is conjectured but not proved is that one geometric quantity, the hyperbolic volume, is controlled by one of the algebraic polynomials. And that's a very famous conjecture called the volume conjecture. So when we asked Mark and Andras, give us a hypothesis of somewhere where it would be interesting if a function existed, their kind of natural choice was, let's see if there's a mapping between the geometry and the algebra of a knot, because none are known. It would be really interesting connecting these fields if it did exist. let's not get our hopes up because probably somebody would have noticed if there was one by now. But whatever, we'll give it a go. So we train a neural network on the geometric quantities to calculate the signature, which is an algebraic quantity. And just to make this slightly more concrete, when we're doing this, we really just have a table of the geometric invariance, and we just list all those out. These can be real numbers or complex numbers or something like this. We just find an appropriate representation and feed them into our network. And there's actually a lot of algebraic invariance. And in practice, what we did do was looked at predicting a bunch of different algebraic invariants, a number of which we could predict with some accuracy, but the signature we could predict particularly well. And the signature is quite a fundamental and like direct algebraic invariant. And we can also calculate it for very large knots, which can be expensive for other of the algebraic invariants. So it was a very natural choice to focus in on once we'd run some of these first experiments.
The geometric invariants, are they all floats,
Are all...
Are they real numbers or complex numbers?
So when we did the Merinal translation is a complex number. A number of the geometric invariants are complex, but we just split those up into the real and imaginary parts.
Sure it was floats or
Yep.
was it rationals?
Yeah, as floats.
That was good enough.
That was good enough.
Because Yangui he was saying on Friday that floats were a disaster.
Yeah, so depends what you're... It depends what you're doing, right? I think one of the reasons the geometric invariants are nice and the floats work here is that things are very smooth. Like things, they are smooth and they vary in a nice way. And this is still something that I haven't really come up with a good short, concise description of. But one of the things that Geordie also mentioned yesterday is it's important to get an understanding of the kind of functions that neural networks are good at representing. And
my takeaway from last week was that floats were not that function.
well, no, I think floats are fine. I can't remember the particular thing he was saying, but...
He was just saying, if neural networks are going to guess stuff, it's the kind of things I want to guess. Like floats are at the very bottom. You don't want to
Floats
guess,
are at the
I
very...
want to guess integers.
Yeah, but the float is the input here.
The float is the input, is that the difference?
It could be, yeah. I do want to remember what that is, but I don't at the moment. So...
There's floats right at the top.
Yeah, exactly. So this is one you saw yesterday. This is just a direct saliency map of which of the features were relevant for predicting the signature. And so this is a nice example because for a number of reasons. But here you can see that essentially we've taken a rather small list in this context of machine learning of hyperbolic invariance, and the network can very easily determine which one of these ones are the relevant ones. But you can imagine we can do this for an arbitrary length of input size. So you could have filtered down from a very, very large set of invariants down to the valid ones. But here, there's 3 that happen to be relevant.
Which are floats and which are integers?
These are mostly floats. The symmetry group is a categorical.
These are mostly floats.
Yeah.
And you're predicting an integer.
Yes.
You're talking about...
Yeah, so we predict an integer from...
dumb thing like, oh, take this bit. It's the irrelevant bit in this float. I mean, it doesn't
No, because it's not given a bit string representation of the float. It really has to, we're telling it to interpret it as a real number.
point at a real vector.
Yeah, exactly. I think, was what you were talking about yesterday with Geordie the parity example? N-dimensional parity? Yeah, so n-dimensional parity is closer to a function which the n-dimensional parity with integer kind of inputs is a hard function for neural networks to learn. So obviously the hardest ones are cryptographic functions because they're designed to be impossible to invert. And they have this function where you change a small part of the input, they're the opposite of continuous. You change a small part of the input, massively changes the output. The floats are good if they represent pretty sensible real quantities because you smoothly vary that a small amount, it's probably going to smoothly vary the output. And even though it doesn't really make sense in this context for knots to smoothly vary the longitudinal translation, you can imagine that doing that a small amount wouldn't change what we think about the signature a large amount. You can imagine there would be functions where that would be true, but in this case, it's certainly not. So these three are kind of relevant, and so then we can take these, show them to Mark and Andras, and try and get them to think about what would make sense. What's a sensible way to combine these quantities, given their understanding of what they actually are, in a way that might predict the signature. And the other reason I kind of like this is because this is data that's been around for quite a long time in the context of things. Low-dimensional topology is a pretty computational area. This data's been sitting around and nobody's noticed this connection. And it's because it sits just above where humans tend to notice things, because this is in 3D. You need to look at all three of these variables at the same time to notice that there is a relationship with the slope. If you look at any pair of them, there's not really an obvious or particularly strong relationship. But if you get all three of them and you kind of plot it in 3D, there's this obvious like twisted plane structure to it. And that's captured by this equation here that Mark and Andras saw the plot, could kind of see what the function was, and then decided what actually made sense in terms of the geometry of the object. And then they came up with a conjecture, because we could plot this and see that it's not exact, but it seems to be true up to some bound. They picked a reasonable bound, tried to prove it for a long time. It turned out not to be correct.
AI could have found that counterexample.
In the right context, AI could have found this counterexample. So it's a very simple, so it's an interesting kind of question that we tested this conjecture across a huge number of knots. So the first 10 million knots, lots of random, very large knots, and it held very well across all of these examples, but there's a kind of measure zero set of particular knots on which this particular conjecture fails. And you can get there from taking any knot and just grabbing two strands and just twisting it like this. And the more you twist it like this, the more it starts to make this conjecture fail. But and so you can imagine an AI could do this if we gave it the concept of a knot and the ability to twist, which we hadn't done. But fortunately, we had Mark and Andras, and they're very good. They noticed this, and there's two different corrections that you can perform to here, one using the injectivity radius and the other using the imaginary parts of the short geodesics of the knot. And these ones they were able to prove, and so we came to the first proof of a connection directly between the hyperbolic structure and the algebra of knot. So we kind of did this, and this is really helpful as a pedagogical example of how we could go about using machine learning to be helpful. So I kind of explained this example to Geordie, and he said, okay, I kind of get what's happening there. The obvious question to look at for him was the combinatorial invariance conjecture. And the combinatorial invariance conjecture is a 40-year-old conjecture, a very central one in representation theory, about the existence of a function. And in particular, it's the existence of a function that maps from a graph to a polynomial. The graph is generated by permutations. So every node of this graph is a permutation, and any edge between two nodes is a simple reflection. So it's taking just two elements in the permutation and swapping them. And roughly this is how you construct the graph. And if you keep the node labels on there, so you know which permutation is on the node, there's a precise formula that just gets you this polynomial. But if you take the labels away, it's long been conjectured you still can calculate the polynomial, but nobody knows how to do it. And so one of the reasons that this problem is hard and that not a lot of progress has been made in the last 30 years is that the graphs, these Bruja graphs as they're called, get very large very quickly. And they're already very large before anything interesting happens. So this is effectively the first non-trivial Kashtan-Lützig polynomial and its first non-trivial Bruja graph. And that's a pretty difficult graph to look at and try and understand the structure and see what's going on. And that's just the single smallest example. Really what you need to do is look across many examples of graphs that are much, much larger than this before you can even see what's happening in the, say, third or fourth coefficient of the polynomial. So they become really huge quickly, and no matter how good Geordie is, he can't look at that many examples of graphs and really be expected to see what's going on. So I'll take a quick detour, because I feel like people are probably familiar with feed-forward neural networks, just to say what's going on if we're using neural networks now to try and learn a function on graphs. And it's pretty simple, actually. So if we do have a graph, one layer that we would call of a graph neural network would look for every node in the graph. There are different versions of this, but roughly what they all look like is for every node in the graph, you would look at messages that come from the neighbors of that node, and you would have a feed-forward neural network that processes all of these messages that are on the edges connected to a node, aggregates it with a function like a sum or a max, element-wise max, and then kind of projects this into a hidden vector, a latent vector, for each of the nodes. And then this is just repeated some number of steps in the same way as you would have multiple linear transformations followed by nonlinearities in a feed-forward neural network. In a GNN, you have multiple of these message passing steps, where at each step you have a neural network that's aggregating information from a node's neighborhood and turning it into a new latent representation for that node. And then after some steps of processing, we can make predictions either about nodes on the graph by just performing a kind of linear transformation or a kind of feed-forward neural network on the node's hidden representation. We can aggregate over all of the nodes and perform a function on that in order to get a prediction on the graph. Or you can kind of aggregate, concatenate the representations of two nodes that are connected to predict information about an edge or a link. So here, we're kind of making a graph level prediction. So we want to take an entire graph, use a neural network to summarize this in some way that we can then predict individual coefficients of the KL polynomial. So the first step, fortunately, is and this part is usually the fast part. Training something and seeing if it can do a good job is not that intensive. So we can train a neural network that can predict these coefficients with accuracy which is far above kind of random chance, and also surprisingly accurate relative to what Geordie would expect. And with a bit of tuning and tweaking, we can get close to above 98%. So for the size of data we have, this is approximately equal to 100 from the perspective of machine learning. Once we have confidence that a function exists, so at this stage we're like, okay, maybe there's for at least 4 graphs up to a certain size, it seems like there's a relatively simple, smoothish function that can predict approximately or exactly the true coefficients. We went through and used the same kind of gradient saliency techniques to try and find information that would help Geordie point him in the right direction to try and find the structure that can ultimately lead to an algorithm to predict this kind of thing. And you've seen this plot before. This was one that, in my memory, I think he told us that can't be true, and we ignored for a couple of weeks, and eventually came back and was like, thought about it a bit more and was like, oh, okay, actually there is something that we could do with extremal reflections that ultimately will let us decompose the graph into something much more structured in a way that he's able to do something with it. And so it follows this same kind of path. We can learn this function, have some confidence it exists, and while our explainability techniques about what's going on in the function are not as developed, I'd say, as the ability to predict functions, they're good enough to get just enough information out to kind of point Geordie in the right direction and fire him off the path to actually prove this in special cases and give us a conjecture that we haven't disproved on any of the intervals that we've actually been able to calculate this on. And we ran this up to as large a size as we could reasonably compute. So that's conjecture generation. And that's a a kind of fundamental part of the mathematical process. But especially given we're DeepMind, people are always like, oh, you should use AlphaGo for something, because it's really good. Maths is just like Go, right? I'm like, fine, okay. So more recently, you would have potentially seen this work come out, and this is about using AlphaGo, some of the ideas and infrastructure behind that to try and also find new results in mathematics, specifically about matrices. And so the particular goal here was to discover new algorithms for matrix multiplication. And if we look through here, sure, everyone's multiplied a matrix at some point, but this is explicitly writing out the formula for a matrix or a block matrix about how you would actually go about doing this and implementing the algorithm of matrix multiplication. And so everyone almost certainly knows the algorithm on the left, which is doing these ones. And possibly a number of people are familiar with Strassen algorithm, which says that you can actually do it a little bit faster than this. You can get rid of one multiplication. And generally, people care about measuring the number of multiplications that you require to do this, because the scaling, when you get up to large matrices, ultimately depends on the number of multiplications, because you can kind of do blockwise decompositions in order to keep this efficiency all the way down. So you save, at 2 by 2, you save one matrix multiplication with Strassen's algorithm, so that's n to the 2.81 instead of the n cubed naive performance that you would expect from matrix multiplication. And that's the, I think, provably best you can do for a 2 by 2 matrix, but usually we care about multiplying larger matrices in 2 by 2. And there's not a lot known about the bounds when we get higher than 2 by 2 matrices. And so we know we can do it at least n cubed, and we know we can't do it faster in classical computing than n squared, because we at least have to look at all of the entries of the matrix. But all we know is that somewhere in between these two pretty obvious bounds. Well, that's not true anymore. There are better bounds than that. But we want to try and discover new constructive fast matrix multiplication algorithms that outperform existing human-designed ones. So one thing that's we'll use in order to get to this matrix multiplication algorithm, and why this is a kind of nice place to start if you're designing algorithms, is that you can describe a matrix multiplication algorithm as a tensor, as a binary tensor, which is essentially describing for every element in the output matrix, so if we've got A times B equals C, for every element in the output matrix, which pairs of elements in the first two matrices are we going to multiply together and then add up in order to get the value in our particular element of the output matrix. And then if we care about how many multiplications are required in the algorithm to multiply these two matrices, that's equivalent to the rank of the tensor. And the rank of the tensor is roughly what you would imagine as equivalent to the rank of a matrix, but the rank of the matrix is easy to calculate. We can just do that, whereas the rank of a tensor, there is no known algorithm for actually finding the true rank of a tensor. So if we can kind of search across this space and find low rank decompositions, then we're actually finding new fast methods for matrix multiplication. And so you can see us starting to build this up into the form of a game that we could play. And so what we could do, you could imagine doing, is taking a binary tensor that represents the matrix multiplication algorithm, and then we want to try and decompose this into a number of rank 1 tensor factors that make up that. And so we can take the original one, and then subtract a rank 1 factor at each step until we get back to the 0 tensor. And then what you would essentially be doing is searching for these rank 1 tensors we want to subtract at every stage and try and get to the 0 tensor as quickly as possible. And that roughly is what I've already described. So just to put some numbers on how this looks as a game, this gives you some sense. This is, I want to kind of say, like super constrained in terms of a mathematical problem, which is kind of why it's maybe the most amenable to this kind of setup. But you can see how the for a 2x2 matrix, 3x3 matrix, 4x4 matrix, and Go, what the episode length is likely to be. So a Go game, you might expect to play about 200 moves. For a 4x4 matrix, we know a good estimate of the rank is going to be 49. So that's about how many steps we should expect if we're like decent at playing the game. The action space in particular here is a lot larger than Go is. So Go doesn't have a lot of moves that you can play at a given point in time. If we're looking at all of the possible rank 1 binary tensors that we could subtract at any given state, that's really large, and you can see the orders of magnitude there. And the observation of the state is pretty comparable to Go as well. So on episode length and observation, we're kind of looking pretty similar, but it's a very large action space compared to Go. And so from a machine learning perspective, there's only one axis of difficulty here that we're changing. And I mean, similar-ish to Go, but maybe a little bit more so than there. There's a large number of symmetries because you can perform like rotations of these tensors and you're not really fundamentally changing the problem. And so we're going to maybe try and exploit that too. So the kind of short version of it is that in some cases, the ML-designed algorithms can beat human-designed ones. And this probably shouldn't be very surprising, because while there is some amount of kind of insight that you can use in order to construct these algorithms, honestly, a lot of it is, you'll see an example of what one looks like, hard to get intuition about, and while there is a little bit of intuition there, it probably involves a lot of search. And there's been a lot of work centered around small matrices of size 2x2 and 3x3, because this is before the problem blows up to a size where it's just infeasible that any human would want to spend any time doing this.
What's important, you know? I mean, this stuff is used, right, by... Which numbers are important? Do we need the answer 1,000 by 1,000, or is 5 by 5 important?
Yeah, so any of these ones actually can be important. So like 3x3 or 4x4 or 5x5, as long as the exponent is one of the important things. Because if we decide, oh, we've got a great like 4x4 or a great 3x3, then if you have a really large matrix, you just do block 3x3s all the way down, and then you get that efficiency up to arbitrary size. So that's one thing. It's all about the exponent. It's all about the exponent in terms of runtime. If we get down to practice, there are actually other considerations too. In particular, numerical stability. So, but that's actually one reason why this can be another thing that's really helpful, because even though Strasson's algorithm is well known, it's not used super frequently because of numerical stability issues. It's not something that you would want to use by default. In some cases, it can be valuable. I don't know if we've got slides on this, but one of the useful things about phrasing this as a game is what they've done here is made the reward for AlphaGo the exponent, like how fast can you actually make this in a scaling sense. But there's no reason that this doesn't generalize very directly to make the exponent large, but also get penalized depending on the either in practice performance, so how does this actually run if you run it on a particular accelerator, or the numerical stability. So we could measure that and actually use that as part of the loss function. So maybe you want something that's as fast as Strasson's, but more numerically stable. You can try and optimize for these different considerations instead. And so if we look at the tensors for which it could find a better decomposition than what was known previously. You'll see that the ones on the far right column are for kind of real valued matrix multiplication. They're all for non-square matrices. So these are cases which have been probably less studied by people in the area. And so the 3, 4, 5 NMP would be a 3 by 4 matrix by a 4 by 5 matrix. Similar for 4, 4, 5 and 4, 5, 5. But there's a new record for square matrices in modular arithmetic, so Z mod 2. And so this is another case where it's something which has probably received less treatment by people studying the area than kind of general matrix multiplication. But the advantage here is that there's a single framework where you can change, changing that once you've got the framework is one line of code, similar to changing what you're optimizing for. And you can kind of just set this and forget it and see what it's able to find. And so, yeah, there's the exponent. If you have 47, then you're at 2.7 for matrix multiplication. And yeah, kind of related to what I was saying, under the hood, this is generating, it's not just a single decomposition of this rank. If it's able to get to a certain rank, usually it can generate thousands of meaningfully different algorithms. So ones that aren't the same up to kind of rotation or something like this, they're actually doing something different. And so there's now you can either, while you are optimizing for something directly, you have a large database of algorithms that have slightly different performance characteristics. So there's also a possibility of combining these in interesting ways. And so this is one of the ones I promised. This is a 4 by 4 matrix multiplication algorithm. No one's going to want to sit there and try and optimize this by hand. But the computers don't mind. We can set them at it, and they'll just kind of tick away for a long time and eventually find something. So I think one interesting observation from this work is that, I'll say at the outset, one of the things that machine learning has, or kind of artificial intelligence broadly, has struggled with for a while is search, or like searching for interesting examples of something, because this sits a little bit at odds of what a lot of techniques are good for. So we're very good at generalizing like within domain, so interpolating functions, not extrapolating functions, and going out and trying to find an interesting example of something that you have never seen before is not usually within the domain of competence of these kind of algorithms. I think this is a big challenge generally, and one of the things which helped a lot in this agent was having it simultaneously train on many different decomposition problems. So different sizes, matrix multiplication sizes, different fields, and have it try and look in these at the same time. So one kind of story you could tell yourself from this is that it's able to find some interesting patterns that generalize between the different problems. And so it can make observations. Maybe it's easier to search through the space of solutions to the 2 by 2 problem that is the 4 by 4. But if you learn something interesting in 2 by 2 that can generalize to the 4 by 4, suddenly you're able to use this to search that space much more efficiently and kind of curriculum your way up in a way which is maybe similar to what some of the talks yesterday were talking about. And so this is just a kind of high-level diagram about how the system works, how the gameplay happens, and this observation that, one, the generalist agent seems to be very important. There was a lot of incorporation of the symmetries of the objects into this problem, so the networks that we used in order to make the predictions that are necessary for alpha 0, which is a prediction of how good your current state is, and as well as a prediction of what, how good a particular next action might be. Those were done with networks that understood the invariances, not all the invariances, but a lot of the invariances of the problem. And to go back to be concrete, if you have a value function for alpha 0 in this case, what you're trying to do is predict the current rank of the tensor that you have. That's kind of your value, because that's how many steps you think you need in order to finish the game, would be your current rank. And then the prediction of the policy of which move to take is which of the rank 1 tensors you think are best to subtract in order to get yourself there. And so you can see the two parts of alpha 0 are you have a lot of actors. So you have a learned policy, which is which is just playing the game, which you give it tensors, it tries to decompose this. First, when you start it off, it does a terrible job, and it eventually starts to learn what's going on, because these played games go then into the learning system, where it's got a kind of buffer of games that are being played, as well as synthetic demonstrations that it started off with. So it's obviously easy to generate low rank tensors that you pretty much know the rank of by just constructing them, taking random rank 1 factors and adding them all up. And then we have this network, which is then trying to predict the value in the policy based on these. And then this is this virtuous cycle where it learns from the games that are being played. The actors then update to the new policy and start playing with the new structure that they've learnt, which hopefully result in better games, which results in a better network. And this is, I think, also what Jordi alluded to, where obviously the networks that we're learning play a big part of this prediction, but it's not just that. There is a learning system in here and a search system, which is the key part of alpha 0, which is really contributing to being able to find these decompositions in the end. And then the final bullet point is always an important one in machine learning, is it turns out if you just throw a lot more compute at it, you're able to find more things, which is not necessarily unobvious, but...
Oh, it is unobvious.
Well, yeah, maybe that's... Thank you.
Tables of elliptic curves and you don't find new things. You've got only
Yeah.
all things satisfying BSD conjecture.
Yeah, okay, thank you, Kevin. So I think this is something that maybe is starting to seem more obvious now, but certainly wasn't to everyone in the machine learning field even 3 or 4 or 5 years ago, that just adding more compute to these problems really would continue to scale without as much of a threshold as we might initially imagine. So yeah, in conclusion, those are two ways that we've found that have started to make progress on interesting mathematical problems, and we're really interested in any further ways that people have to make progress on this problem. So thank you very much.
Thank you, Alex, for a great talk. We're going to have some questions from the audience. Yes.
So I have a question regarding the saliency maps. So for example, for the computer vision, you showed that the salience map kind of concentrates on the cat.
Thank you, my favorite slide.
So
You can keep going.
So I was curious, did you try to do similar things for like the stuff that help you with conjectures, like when you use deep learning to predict the polynomial for the Bruja graphs? Did you look at the saliency maps to see on which areas it concentrates in the graphs or things like that?
Yeah, absolutely. So in both cases, we used exactly this technique, and it doesn't look as cool as the cat, obviously, but here, this is how this graph is generated. So each of the features on the y-axis is one of the inputs, and then the normalized attribution score is the kind of averaged over all of the data, the norm of the gradients of the features with respect to the output. And then in the case of representation theory, I actually didn't have one of the plots in here, but there's, what we essentially did was the same thing. And if we look at these graphs, because of this structure, at the prediction, we can kind of go all the way back and take the gradients of any of the nodes or the edges with respect to the predictions that we make. And we first noticed essentially some structure in the edges. It's kind of first order neighbors and diamonds. So we're looking at across all of the graphs structurally which edges are interesting, and there's kind of some structure at the base that we noticed first and could show Geordie just from kind of individual plots of the graphs. And then the second thing we did was go and look at different ways to aggregate these saliency maps in ways that could be meaningful. And one of them was this plot where every element of that heat map is one of the types of edges. So I kind of mentioned in the intro that all of the edges there are a simple reflection, which just swaps two parts of the permutation. And so we get one of these graphs for every symmetric group that we looked at. So this is for S9. So the symmetric group are 9 elements. So you've got every element 0 through 8. And the particular observation here is that the ones that in blue turn up much more frequently than one would expect statistically, and the red ones much less. And all of the red ones have a name. They're called simple reflections, which are reflecting neighboring elements. And these are very fundamental to the idea of a Bruja graph, and it's very reasonable that these might be special in some sense. But the ones along the left axis and the bottom are ones that involve 0 and 8. And those ones are called extremal reflections because they involve one of these elements on the edge. And this is a very natural type of reflection to consider in representation theory, but it wasn't at all obvious that that had anything to do with what we were looking at. And so while this didn't really mean a lot to me, it was obvious that there was some structure there. And then Geordie could say like, oh, okay, well, if I was forced to try and think about how would I use extremal reflections in this problem, that's where this kind of mysterious term in the equation he showed yesterday came from.
Thank you.
I have a question on the first problem, on the not problem. You mentioned before that one conjecture was false. Yeah, you passed. Yeah, exactly. This one. Is it possible to like? I mean, you mentioned that like for this conjecture, like you spent like 10 millions of experiment, and then you saw that like this conjecture was false, and then the theorem that you proposed was another one. Is it possible to even expand it? And also, is it the inequality that you show sharp enough? So like, do you do any additional work to see if you can find some counterexample of a bit more large inequality? What I mean is, like, if you add like a +1 term in some sense, would it still would the inequality be applied? And
yeah, I think so. If I interpret this correctly, you're saying, you know, is this bound like sharp and interesting? Like, and can we kind of tighten this bound up? And can we use machine learning to kind of help in this procedure? Yeah. So the first one was incorrect. The one we mostly talk about here is the one with the injectivity radius, and we've kind of empirically then looked at this over again, as larger knots as we can actually generate and calculate these quantities on. And there's another sneaky way that could be bad. Like C3 could be like arbitrarily large. So C3 it seems in practice very small. So C3 was like, we could estimate it on the knots that we can actually see, which is not, again, this is only empirical evidence. It's like 0.2 or something like this. And if you look at these bounds, they're pretty tight. Like the volume increases linearly with the crossing number generally. And I personally don't understand the behavior of the injectivity radius as well as the collaborators, but this was, in some sense, their favorite version of the formula because it says something quite interesting. The other one that I mentioned that involves the correction terms based on the short geodesics, I think is a lot tighter, but it's a more involved correction term, and I think it's a little harder to prove, and for whatever aesthetic reason, they didn't prefer that, even though it gives you a slightly better bound. And but I think it's really interesting to get into that because this has been mentioned before, and what we've highlighted up here is that, you know, when we first showed the saliency map, we're like, okay, these three are clearly the ones that we should focus on, and we should ignore everything else because it looks kind of like noise. And statistically, those ones in the cusp volume are not noise, but we're like, they can't be that interesting. Just ignore those. And one of the reasons that that is the case is because they're relevant for the thing we're trying to predict, but we weren't actually trying to predict the bound. And this is, I think, a kind of, in retrospect, a bit of a mistake. We were just trying to predict the function as well as we could. We weren't also trying to predict the error. And so I haven't even done that experiment. I haven't gone back to see, like, okay, can we predict the absolute value of the residuals with some of these other things? If so, you know, the injectivity radius and the short geodesics would obviously jump out, but I don't know if any of the others would. Probably, I think given they've looked at it seriously now, I don't think it would, but that would be the natural next step we should have done.
Thanks for your talk. It was really interesting. I have a question on the matrix games work. So do you have a sense of how the compute requirements will scale if you were to start searching for more efficient matmoles for matrices that are a few orders of magnitude larger?
Yeah, that's a really good question. So pretty much, as you might guess, like we're running this up to the 5x5, and that's pretty much capping out what we can do. Like it's not really tenable to go with this particular setup much higher than 5x5 because the scaling of the size of the tensor grows very fast with respect to the size of the matrices you're multiplying. So I don't think I actually mentioned it, but for a, say, 5x5 matrix multiplication, the tensor is 5 squared by 5 squared by 5 squared. So you kind of get this n to the 6 tensor that you're looking at. And so the compute for even starting to look at that tensor, as well as how much harder that makes the learning problem, means that for this particular setup, maybe if you pushed it, you could go a couple bigger, but I wouldn't imagine too much more than that unless you start to do something a lot smarter or different.
Thank you.
All right. When you input the numbers, do you have an embedding layer, or you input just the numbers as them?
In the networks, when they're trying to make the predictions of the kind of value function, the policy function?
Yeah. I mean, from the start, like in the language models, there's like embeddings for each letter or word.
Yeah, that's true. I guess in some sense you do have an embedding, but in this case, it is true. Wait, hold on. Is it true as we're actually decomposing the tensor? Originally, the tensor is binary. I don't necessarily know that it stays as you go along. I'm not 100% sure off the top of my head. I'll look into that and get back to you.
The question is, do you look at the numbers as they are, or do you represent them for a higher dimension something?
Yeah, okay, I can at least address this, like, because I think this is interesting and related a bit to what Kevin was talking about before. It's like when you have a number, like how are you looking at it is very, very important. And in this case, I would assume that we really want to look at the numbers categorically more than forcing them to interpret them as real numbers or integers, just because there's not a lot of different possible values there, and it's not clear that the smoothness, like if I have a big tensor with some ones and some zeros and some minus ones around the place, like for all intents and purposes, I could probably just consider those 1 and minus 1 as unrelated symbols, like in a language modeling, as you say. So my guess is that's probably what was used here.
Do you have any comments about this Cowers and Moose power?
Who, what's the cows?
They were a couple of...
Oh, this was the one that came out like a couple of days later. Yeah.
Beat one of your
Mm-hmm.
like 2 weeks.
Yeah.
It just only ever feels with two unknowns.
Yeah, exactly. So
I
yeah.
have a front page.
Yeah, exactly. Yeah, so it's like a week later, someone comes out and they're like, oh, okay, we've taken the tensor that DeepMind's found, and then they found one rank better again. So,
in a special case, right?
in a special case. Yeah. So it was this, I think it was the square one, probably. I think, yeah, it's like it's the 5 by 5, the 96 one over the modular field. And so this is really interesting because obviously the network's been able to do a pretty good job of learning this and has spent a lot of compute and got down to 96. And so you think maybe that's as far as it can go, maybe that's a reasonable bound. And then there's a couple of guys who've done something orthogonal to what was going on here, and were able to get this down by another step again. And I think that we're still waiting to find out what they were doing. I think they just said we used like the kind of tensor example that's in the paper, and then we did something to it and we got down another level too. So, I mean, since we don't know what was going on there, I think the takeaway from there at the moment is that like this kind of search procedure does not dominate like all possible search procedures. And I think that what I said earlier still holds in that searching, like there's definitely ways to do it. It's gotten better and better over time, but it is still has this feeling of something slightly unnatural for machine learning to be doing, to be searching for new things of which it's never seen stuff before. And so I think would probably be something to be learned and incorporated into the search if and when we know what was going on there.
All right, if there are no more questions, let's thank the speaker again.
Yep.
Testing.